In this question, they state it rather simply, but it turns out to be a little bit complicated. First of all, this drawing's pretty bad. What it should be is we have one ball coming in here, and all three of them are identical, so they should be the same size. And due to symmetry, that is, if you put three balls together, we should get a pattern that's very regular. So regular, it's called an equilateral triangle. Now these dots here represent the center of these circles. So here, we would have the angle each time as 60 degrees. So we can save a lot of work just looking at symmetry. Furthermore, we'll have this ball move off this way and this ball move off this way. Now that might be 60 degrees angle with respect to each other, but that means if we trace a line in the middle, that would be 30 degrees and 30 degrees. And that's useful for us to know because we're talking about this line to start off with. This ball comes in, or this spaceship comes in on this line, and these two go off at 30 degrees angle. So afterwards, we'll have something like this. We'll say that the first spaceship keeps on going in a straight line. It either will go in a straight line or will go straight back. One of the two. Can't go off to one of the angles, that is up or down, because, well, by symmetry that wouldn't make any sense. Why would it choose up rather than down if it's equal here? So afterwards, the spaceship will say go in the positive direction with some speed v. If we're wrong that's going in the positive direction, then we'll just get a negative answer. Then we'll know to flip this vector. And also we have two balls that are going off at 30 degrees angle. But what we can do, okay, and we'll say this is speed u, we can just talk about one of these twice, because by symmetry the component here will be the same for this bottom ball as it is for the top ball. Okay, let's use one of our conservation laws. Let's start off with conservation of momentum. So our momentum to come in was 20 m, where I'll say m is the mass of one of those spaceships. And that's all. The other two weren't moving, so of course they didn't have any momentum. So we have the speed and the mass here. Or you can think of it as velocity if it's speed in this positive direction. Now that will equal everything that's happening later in terms of momentum. So we have this one, our spaceship that hit the other two. That one will be simply Vm. And then we'll add to that 2 mu cos theta. Now again, I said we have two of these spaceships, so that's why we have a 2 here. We need the mass of the spaceship, and here this u cos theta, that is the component along this line of that spaceship's velocity. We can simplify this one a little further. We can get rid of m because that's in every term, so we have 20 is equal to v plus, okay, we get rid of that m, but cos theta, well, in this case, really, I should say cos 30 degrees. Cos 30 degrees is equal to the square root of 3 divided by 2. We have a 2 there. So this turns out to be just u and then the square root of 3. Okay, and that's as far as we can go. We've got two different variables and we have one equation. That's not very helpful. So we need to get another equation. Okay, well, these are hard spherical spaceships. That means that the collision here will be elastic, so our energy will be conserved. And the energy we're talking about here is kinetic energy. So for a second equation, we'll start off with kinetic energy, and that was, this only had kinetic energy, so that was half mass of the spaceship times 20 squared is equal to half m, the speed later, squared, plus we have two of these, so 2 times half m u squared. This time we're talking about the actual speed of those. We need to use speed, not the component along this direction, so that's why there's no cos 30 there. Now this one we can simplify still a bunch. We can take out all of these halves, and as well we can take away the mass because that's in each term. So we get 400 is equal to v squared plus 2u squared. Okay, and that will make our second equation. So at this point we have two equations and two unknowns. So really we're just doing an algebra question right now. The way I would solve this is I would rearrange this equation for u equals. So here u is equal to 20 minus v, and then I'll have still that root 3 there, so divided by root 3. Now I want to put that into this equation, but I have to be careful because when I square this top term, I can't just simply say 400 minus v squared. That would be wrong. I need to have 20 minus v times 20 minus v. So that will look like u squared is equal to 400 minus 40v plus v squared divided by 3. Can't forget to square the denominator as well. Putting u squared into our second equation gives us this. 400 is equal to v squared plus 2, and then the u squared is 400 minus 40v plus v squared divided by 3. Okay, I want to get rid of this fraction, so I'm going to multiply everything by 3. So this by 3, this by 3, this by 3. So I'll have 1200 is equal to 3v squared. So that 3 is now gone. And then I can spread out this. I can say that's plus 800 minus 80v plus 2v squared. Continuing, I can move this 800 to this other side, so that gives me 400. My v squareds, I can put them together, 5v squared, and then I have 80v left over. Divide that by 5, I have 80 is equal to v squared minus 16v. If I rearrange that, I'll have this quadratic equation, which I can also factor with v minus 20 and then v plus 4. So that gives me the solutions. Either v is equal to 20, because this is of course equal to 0, or v is equal to minus 4. So it says this will work in two cases. Well, v equals 20 was our initial case. That's what was happening. The spaceship was coming in at this speed. So that is not the answer we're looking for. We're looking not for before the crash, but after the crash. And that says minus 4. And so that means that we were wrong. When we said that the spaceship would keep on going this direction with v, no, not that way. It would go backwards. It would go backwards at 4. And that would be answer D.